Hello, this is Anthony Molinares with Masaki Morrow, Caden Jones, and Denny Reyna, and this is our boat trip project for Group 6.
All right, to start off, we're going to talk about what our project is about. We're going to mainly focus on the development of reliable and effective marine mechanical equipment. Our goal is to improve the durability and efficiency of machinery designed for use in harsh ocean environments, whether at the surface level or deep sea. This work usually sits at the intersection of chemistry, ocean, and mechanical engineering. Chemistry plays a crucial role through material science, such as like choosing the materials. It also plays a role through chemical reactions. So choosing the materials that would
Sorry, hold on.
withstand the corrosion the best for any equipment, especially after prolonged exposure to salt water. The illustration here is our oil rig right here. Oil rig faces extreme oceanic conditions every day. It's constantly exposed to seawater, pressure, various chemical reactions, which obviously weakens the structure and integrity of the materials over time if not properly engineered. This is why our project focuses not only on the mechanical design, but also the chemical resilience of the materials we use.
Our project consisted of four members: me, Denny Reyna, the team facilitator; Masaki Moro, the project manager; Kaden Jones, the research facilitator; and Anthony Molinares, the team manager. The situation that challenged us was finding appropriate times to meet. To overcome this, we fell back on our agreement to simply sit down for at least 5 minutes and discuss the solution. Our agreement was very effective in helping us, and we often found a time to meet sooner or later.
Okay. Initially, our ideas consisted of tackling first corrosion, then waterproofing and pressure, and briefly we considered looking into navigational systems on sea vessels as well as sustainable energy produced by the ocean and the desalination of seawater. But finally, we realized that several of these were actually smaller parts of a larger issue, and some of the biggest threats to the structural integrity, mechanical efficiency, and longevity of mechanical equipment in and around the ocean uh, are corrosion, poor hydrodynamics, pressure, and insufficient waterproofing. So, our final problem was finding and researching preventatives to all four of these to ensure reliability and longevity of mechanical systems in and around the ocean.
Just before we move on, I'm going to talk a little bit about our findings. We found out that corrosion, hydrodynamics, waterproofing, and pressure would be main areas that us mechanical engineers can talk about in this marine field. One huge example was the towboat we found across our boat trip. It relates to all four of these the most, in our opinion.
Yeah, and if you also remember, it was the towboat that reminded us about the importance of hydrodynamics because the super flat shape was making huge wakes in the water. Alright, all mechanical equipment in or around the ocean is at risk of damage by corrosion. Firstly, the forming of rust poses a significant threat to mechanical equipment near the ocean, so any piece of machinery that is intended to function near the ocean for any prolonged period of time should be built with this in mind. A simple preventative to rust, according to the American Galvanizers Association, is hot dip galvanization, as outlined in their article, What is Galvanizing? Essentially, the steel is dipped into a molten zinc, forming a tightly bonded alloy layer that will corrode before the steel, shielding the rest of the mechanics. Underwater, however, poses a different threat. Galvanic corrosion can occur when two dissimilar metals are submerged in a common electrolyte, in this case seawater. This type of corrosion can also be solved by an insulative layer, but as the article Cathodic Protection Explained states, a cathodic protection system can be installed. This system involves another charged metal to act as a lightning rod of sorts to corrode instead of the actual components of the machinery.
Another key factor is optimizing the hydrodynamics of the machinery. At sea level, water is 800 times more dense than the air. This means that the machinery experiences substantial forces just from the sea alone. The article by the contact patch describes the relation between the coefficient of drag and the geometry of the object. They say that the most optimal shape is the teardrop, and a good example of this is a submarine, which is designed for deep water expeditions. But this is not only for vessels, but it can also be for stationary machinery as well. And according to the US Department of Energy, 99% of current offshore wind energy comes from fixed bottom turbines. And those are wind turbines with their structures built directly into the seafloor. And the cylindrical shape of the structure is optimized to lower the amount of force that the turbine experiences. And researchers in the field of fluid dynamics utilize fluid simulations to understand and optimize these geometries. And so overall, optimizing the hydrodynamics can improve the machine reliability.
Although sometimes overlooked, waterproofing is another key problem to understand when designing machinery and selecting appropriate materials for vessels. Throughout a ship's lifetime, its risk of water breaching through seals or cracks continues to increase. This causes deterioration of needed machinery and corrosion for the vessel. Not only this, but the deteriorated ships can begin to pollute marine environments in many different ways, whether that be in the spillage of important materials being carried or the overall disposal of parts because they were destroyed in the process of seawater leaking in and damaging parts. According to IMC distributors, a common method of waterproofing we can use in response to these issues is the use of protective coatings such as polyurea. This is a very versatile material used in a variety of settings, such as buildings, machinery, and boats/vessels. Not only does it protect surfaces from water, but it is able to work as a sealant, resist extreme temperatures, and protect from UV radiation. As mentioned by Technopool, polyurea is very strong, but depending on its chemical composition, it can have the opposite effects. Rather than protecting and sealing, an aromatic structure of polyurea would make surfaces more prone to deterioration and overall shorten the lifespan of materials vessels are made of, increasing possible leaks. A firm understanding of waterproofing, chemistry, and engineering is essential to creating functional equipment and vessels.
Let's move on to pressure in the context of marine/mechanical engineering. Specifically, though, we're going to look at the materials responding to tension in high pressure environments. First, let's talk about the ultimate tensile strength, which is basically the material's ability to resist tearing when it's under tension. You can see right here the metal stretching out where it starts to narrow neck or just before it breaks. This demonstrates the limits of what the material can handle under extreme conditions. Right here we have Barlow's equation. This is used to calculate internal pressure. This equation helps engineers determine the internal pressure that a vessel can safely withstand. It's more or less for cylindrical vessels such as pipelines, submarines, even wires. The maximum pressure it can handle before it fails is known as burst pressure. When pressure exceeds this limit, failure occurs, such as the explosion right here of the submarine. It can be explosion or implosion. One approach to manage the burst pressure is by increasing wall thickness. Thicker walls add structural strength and help resist higher pressures, though there's a trade-off. Too much thickness is weird, silly, it's impractical. It's adding weight and cost. So, engineers must be careful when balancing the three main factors of strength of the material, the thickness, and the budget. This balance is key to designing reliable underwater machinery. Looking at the graph here, you can see where materials reach their breaking point after a certain level of outward pressure, with a mix of strength of material and the wall thickness to determine when it'll start to neck.
An additional finding from our research is this towboat that sank in the summer of last year. The reasoning for the capsizing was from an undetected corrosion that led to watertight integrity issues. And this relates to our topic because it deals with two of our solutions of preventing corrosion and improving waterproofing. And it also relates to our towboat finding from the boat trip. And these wreckages negatively affect the marine environment because these vessels release oil and heavy metals into the ocean. So our solutions for improving the design of the machinery is important to prevent these kinds of accidents.
And finally, here are all of our references. We do have them on our individual slides, but we also have them all collected here together on this first slide and the second.